Today, we're diving into something that sounds, well, pretty much impossible. We're talking about a brand new scientific method that claims to have created a map for chaos itself, a way to forecast incredibly complex things, from wild weather patterns to even crazier market swings. So, let's get into it.
I mean, it's a fair question, right? Think about it. We can pinpoint the exact moment of an eclipse years, even centuries from now. But trying to figure out if it's going to rain 3 weeks from Tuesday? Good luck. The difference comes down to one little word: chaos. And as we're about to see, a particularly nasty type of chaos. So meet the final boss of forecasting: hyperchaotic systems. Now, deterministic just means they're not random. They do follow the laws of physics. But, and this is a big but, they have an extreme sensitivity to initial conditions. You've heard of the butterfly effect, right? A tiny, tiny change at the start can lead to a massively different result down the line. Then you add in high dimensionality, which is just a fancy way of saying there are a ton of different variables all interacting at once. Put it all together, and you've got a recipe for something that is almost impossible to predict.
Okay, so we know these systems are a tough nut to crack, but why exactly do our standard go-to forecasting tools struggle so badly? Let's take a quick look at the two main ways we've been trying to do this, and see where they just fall apart.
So, on one side, you have your classic local linear models. These try to cheat a little by just assuming the system acts in a nice, straight line, at least for a very short moment. The problem? Well, as the paper points out, chaotic systems are anything but linear. They're curvy and wild. This oversimplification means the errors can just blow up exponentially, a problem that scientists literally call exploding. Not good. On the other side, you've got machine learning. Super powerful, right? But it's often a total black box. It can spit out an answer, but it won't tell you how it got there, which is a huge problem when you're trying to actually understand the physics of what's going on.
So you're basically stuck between a rock and a hard place. You either use a model that's way too simple to capture the real, complex dance of the system, or you use one that's so complex it's completely unexplainable, basically ignoring the very dynamics you're trying to study. You can see why we might need a totally new way of thinking about this.
And that is exactly what this research delivers. This is the big idea, the breakthrough at the heart of the paper. Instead of trying to force chaos into a straight line or a black box, these scientists decided to do something completely different. They decided to draw a map.
Now, this quote from the paper really gets to the heart of it. What they're doing is taking a time series, which is just a long list of data points over time, and they're using it to build a network. This network acts like a simplified map of the system's attractor. An attractor is basically all the states and pathways that a chaotic system naturally loves to follow. So they're not trying to map every single possibility, just the system's favorite hangouts and the main roads between them.
The goal here is so intuitive, it's brilliant. It's to chart the highways and the most traveled backroads that the system uses over and over again. Because if you can build that map, well, predicting the future suddenly becomes as easy as finding out where you are right now and just seeing which road is the most popular one leading out of town.
So, how on earth do you actually build a map like this from a chaotic jumble of numbers? It sounds incredibly complicated, but the process is actually super methodical and clever, and it breaks down into a few key steps.
First, they simplify the data. Imagine you take the full range of every possible value, from the absolute lowest to the absolute highest. They just chop that entire range into 64 smaller buckets. Then, for every single data point, they just replace it with a symbol, a number from 1 to 64, that says which bucket it fell into. It's kind of like turning a super high-res photo into a more pixelated version. You lose a little bit of detail, but the main structure, the big picture, is still there.
Okay, so now you have this long string of symbols. The next step is to look for short-term patterns. Instead of looking at just one symbol at a time, they group them into little bundles, which they call vectors. This is kind of like going from looking at individual letters to actually reading short words. It gives you a snapshot of not just where the system is, but where it's just been.
Next, they build the locations for our map. So, if symbols were letters and the vectors were words, this step is like identifying common short phrases. Each one of these unique phrases, which represents a short piece of the system's journey, becomes a node. Think of it as a single town or landmark on our map of chaos.
And finally, they connect the dots. I mean, literally. If they see the system move from one of these nodes to another, they draw a line between them. And here's the really clever part. Every single time the system takes that exact same path, that line gets a little bit thicker. This edge weight reveals the most probable routes, creating those well-traveled highways on our map.
And just like that, with the map fully built, Making a prediction becomes almost ridiculously simple. You just find the node that represents what the system has been doing most recently, you look at all the paths leading away from it, and you bet that it's going to take the path with the thickest line, the most traveled road.
It's a really beautiful idea, isn't it? But the only question that really matters is, does it work? Does this new map actually lead anywhere useful? Well, the researchers put their model to the test against some seriously tough hyperchaotic systems. Let's see how it did.
Okay, whoa. Just look at this slide. This chart shows the prediction error, and it's not even a fair fight. Look at the error for the traditional linear model. It's huge. Another network-based model is also really high. But then look at the new method. See that tiny little bar on the left? That's it. This isn't just a small improvement. This is a whole different league.
And it's not just more accurate, it stays accurate for way, way longer. The paper shows that for several of these systems, the predictions from this new map stayed reliable for up to 40 time steps into the future. In the world of chaos, that is an absolute eternity. Most models fall apart almost instantly. And this wasn't some lucky fluke.
Yeah, this wasn't a one-and-done kind of thing. The researchers threw everything they had at it. They tested it on 3 different hyperchaotic models, each one getting more and more complex. We're talking 4, 5, and even 6-dimensional systems. And in every single case, their new network model was the undisputed champion. It proved to be incredibly robust.
So, okay, we've established it gives us a much better forecast. That's great. But the true importance of this, the reason this research is so exciting, goes a lot deeper than just getting the right answer more often.
Here are the real takeaways. First, and this is huge, it is not a black box. Because the map is built right from the system's own behavior, it's a model based in physics. That means it naturally captures the underlying structure of the system, that attractor we talked about. This is what helps it avoid those runaway errors that kill linear models. But most importantly, it gives us real, genuine insight into why the system is doing what it's doing.
This final quote from the paper just nails it. This tool isn't just for predicting things, it's for understanding them. By creating a map of this chaotic behavior, we get a brand new window into the fundamental rules that are running the show. It lets us finally see the pattern hiding in all that noise.
And that leaves us with a really fascinating thought to end on. We now have this powerful new lens for looking at incredibly complex data. So the big question is, what's next? What hidden highways and predictable patterns are just waiting to be discovered in the chaotic data of our climate, of our biology, or even our financial markets? With this new kind of map making, we might finally have a way to find out.